Hi everyone, here's our second part of our very last video on astronomy. And this video deals with Einstein's general theory of relativity. To summarize this theory of relativity, we could say that observations made in an accelerated frame of reference cannot be distinguished from observations made in a gravitational field. So pretty much what that means is that acceleration feels and acts like gravity. And unless you can look around and see your surroundings, whether you're feeling acceleration or whether you're feeling gravity cannot be distinguished. They feel identical. Okay, what are we talking about here? Okay, so imagine a couple of experiments. First, put yourself in a box like this guy here on the left. It's a room with no windows, so that's a key. You can't see what's happening outside of the room. And in the room, it looks like a weight or a box or a purse, whatever the heck that is, and you're just going to let go of it and it's going to fall. You're going to see this box hit the bottom of the floor and you're going to say, hey, I must be on Earth. Gravity is pulling that down. Okay, and then you fall asleep and you're still in this room and you didn't know it, but someone put you in outer space. They wake you up at the same moment they fire the rockets. So there's no gravity. You're way out in deep outer space, not near any massive object, so there's no gravity. And they fire the rocket, and now the rocket ship is accelerating in this direction, and you're not holding onto this purse. And you see the purse hit the bottom of the floor. What's really going on is if you could look from the outside, you would see, with the X-ray goggles, you would see that purse or whatever it is would be standing still because it's not attached to anything. And as the rocket ship fired its rockets, the whole room and yourself would move forward or up in this sense, and move up, and the purse would remain motionless because of Newton's first law, right? An object in motion stays in motion, or an object at rest stays at rest unless acted upon by an external force. Well, what's going to happen is the room is going to go up and slam into that purse. But from your point of view, you feel the floor pushing against you. The rocket ship is pushing the floor up against you, and you're being accelerated. And to you, it feels like it's gravity that's pushing up on you. Your inertia wants you to hold still, and your weight is going down as the ship pushes up, right? So equal and opposite forces there. And you're going to watch that purse slam into the bottom of the floor. And what's really happening is the floor is slamming up into the purse. But unless you can look outside, you can't tell a difference. This is acceleration on the right. This is gravity on the left. And within that room, that purse is going to fall the same way. You can't tell them apart. Okay, one more example. Okay, so now you're in this room, and you fall asleep, you wake up, and you're floating around. And you look at the purse, you look at yourself, everything is suspended, and you say, whoa, I must be in outer space. Sure, that might be the case. And here in outer space, there's no gravity, so there's no acceleration. But something else might be happening. You might be in free fall. So if there's no windows, you can't look outside to see what's happening. But if you're freely falling, the room and yourself and the purse, they're all heading towards good old planet Earth at the same rate, same acceleration. And so between you and the floor, you're not approaching or moving away from that. And so relative to the floor, you're not being accelerated. The floor and yourself are moving at the same speed. You're both just motionless. And it acts the very same way as if you're in deep space with no gravity. But you are in gravity, right? You're in free fall. So you can't tell the difference between no acceleration on the left and acceleration on the right. It acts like there's no gravity in both cases. Okay, so that's Einstein's general theory of relativity, is that gravitational fields feel the same way, act the same way as being accelerated. Okay, what does this really mean? Well, we live in three-dimensional space. So there's length, width, and height. Those are the three directions, giving us three dimensions. And then we also live in a place where time flows in one direction. So that's another dimension. And altogether, that gives us 4 dimensions of our universe. And we call our 4-dimensional universe space-time. So it turns out that's a part of Einstein's general theory of relativity, is that both space and time are interconnected and actually are just one thing. And then, here's the cool part, mass has the effect of curving space-time. And gravity or gravitational effects are a consequence of this curvature of space-time. So what do we mean? Well, the old way of doing the projectile motion would be use Newton's law and say that, hey, shoot a cannonball out, and there's a horizontal component where the inertia says an object in motion continues in a straight line path unless acted upon by a force. And then there's a vertical component that says gravity is going to pull down on this cannonball and make it go in a curved trajectory, a parabolic trajectory. That's the old way of doing it. Einstein's new way is that the planet, the Earth itself, is curving space-time. And so when you fire this cannonball, it's just going to follow the curvature of space-time. I know, that sounds weird. Okay, well, let's try this example then. Here we have the sun, and maybe it's during a solar eclipse where the moon is blocking part of the sun, or all of the sun, so we can look pretty close to it. And maybe in the distance there's a star that happens to be on the other side of the sun from our point of view. And it turns out we can actually see the image of that star because of gravitational lensing, right? So the gravity of the sun is going to pull on the light and bend it or refract it back towards the Earth so we can see the image of that star. Now that's the old way, the classical way of explaining the physics of gravitational lensing. The new way, Einstein's general theory of relativity, is that the sun's own gravity is curving space-time. So that's what this grid is supposed to be. A flat grid over here is not curved, but in the presence of the gravity of the sun, the mass of the sun, space-time is being curved. And now all this light is doing is following the shortest path through curved space-time. And so the path itself will be curved and make its way to the Earth. Okay, so that's kind of weird, but it can get even more weird because space and time are interconnected into one thing, space-time. Well, it isn't just space that's going to get curved. Right? So this diagram shows kind of the grid of space being curved. Well, it's not just space, it's space-time that curves. So time itself is going to be curved. And what does that mean? Well, Einstein's general theory of relativity predicts that time will be slowed down by massive objects. So gravity itself can slow down time. And Einstein's general theory of relativity has been tested many times. You have to make ultra-precise measurements, but they've been verified. If you take a clock and watch how fast that clock runs at the base of a tower, which is closer to the center of the Earth, so the gravitational effects are stronger, it runs slower than if you take that very same clock and move it up to the top of the tower. So it helps to have a really, really tall tower so that you can get farther away from the center of the Earth where the gravitational force is weaker. Not that much weaker, but measurably weaker. And it turns out, yeah, the clock actually runs a little bit faster higher up, where it experiences less gravitational force. So mass, the mass of the planet Earth, can actually curve space-time, resulting in clocks that run slower, where there's more curvature, where there's more mass. So this poor guy's watching the clock slowly move. Yeah, try going to outer space. The clock will move a little faster. Okay, but let's go back to the first thing we said about general theory of relativity. Observations in an accelerated frame cannot be distinguished from observations made in the gravitational field. So, we said time slows down in the presence of massive objects, in the presence of a lot of gravity. Well, The general theory of relativity says it doesn't matter whether you have a lot of gravity or a lot of acceleration. They're both going to curve space-time. And a lot of gravity or a lot of acceleration means you're both going to slow down time. So there's something called the twin paradox. And that's where you have two twins. They're of the same age. That's the definition of a twin, right? And one of them becomes an astronaut, climbs an aircraft, and goes for a long trip. And so let's describe that trip made by the twin that stays behind on planet Earth. Well, what he's going to observe is that the rocket ship with his twin brother is going to take off. It's going to start at speed of 0 miles per hour, launch in orbit, and now let's say we have the technology that make that rocket ship go almost the speed of light. Remember, C stands for the speed of light. He's going to experience a huge acceleration. So that's just like being next to a very massive object. It's going to slow down time. Now, this twin on the planet Earth is not being accelerated, so he feels no time dilation. He just watches the astronaut take off, make it to, let's say this star called Vega, which is 25 light years away. Well, if he's traveling at almost the speed of light, it's going to take him about 25 years to get there. And then he's going to have to slow down. So maybe he's not going to come to 0 miles per hour, but he does have to change his direction. And that's going to take acceleration, right? Velocity is a vector. To change direction, that takes acceleration. That's going to slow down time. And then when he approaches Earth, well, he better slow down or else he's going to crash land. So he has to slow down. That's also acceleration. I guess maybe it's called deceleration, but it's still a type of acceleration. Okay, the round trip takes 50 years if he goes at the speed of light. Now for the astronaut, he experiences the acceleration and the time dilation, meaning time's going to slow down for him. It's going to feel like it takes about a year to go to Vega. The net result is the astronaut feels like and actually experienced only the passage of 2 years of time. So he's just a little bit older. His twin brother, though, waited on planet Earth for 50 years. And so now they're not the same age. And in effect, the twin brother, the astronaut, effectively time traveled. He went into time 50 years into the future, but he only aged 2 years. Pretty neat stuff, huh? We'll talk more about it in class.